In Chapter 2, we're going to cover a little bit about some basic chemistry. Now, this is not a chemistry class, and so we're just going to hit some of the highlights, some of the important areas, I believe, that are important to biological organisms as we look through chemistry. But it is important, I think, to kind of go through some of the aspects of chemistry because, after all, living organisms are, a collection of cells containing many different chemicals, and those chemicals are reacting, going through different types of metabolic reactions. So it doesn't matter if you're talking about living organisms such as bacteria or plants or some type of fungus or even animal life, humans. We're all chemical, areas that we're all made up of cells that are performing many different types of chemical reactions. So it's very important to understand a little bit about some basic chemistry. These are some of the main topics we'll cover in Chapter 2. I think it's good to understand what an element is, what are atoms, what happens when you combine those and make molecules and compounds. Water is a extremely important substance that we're going to talk about. Technically, it is a chemical, and so it's extremely important and has some very special, I guess you could use that word, qualities about it. And so we need to look at some of those characteristics of water that really stand out and make life possible. And then at the end, we'll talk briefly about what an acid is and what a base is. So some of this is probably review. You probably have seen many of these terms somewhere along the way if you had some either basic chemistry, basic biology, high school science classes, physical science. You probably have seen some of these terms before. A lot of it is basic definitions, vocabulary. So again, make sure you find some way to really understand the vocab, highlighted words, and the bold-faced words. Make sure you find some way to really get a grasp on these vocab definitions that you'll see, such as number one, matter. Anything that has mass that you can measure that mass with, and it occupies some type of space. And matter comes in four main states, although we really, as far as living things, really talk about the first three, solid, liquid, and gas, although there is technically plasma as well as a state of matter. All matter, whether it's living and non-living, are made up of those elements, and we're going to give you some examples of those. Your book definition for an element is there for you: a substance that cannot be broken down into substances with different properties. Essentially, it's composed of a single type of atom. And so if you had some carbon, it's basically made up of atoms of carbon, and it would be a pure or just a complete setup of atoms that were all carbon atoms, and that would make up that element. If you changed anything about that atom, maybe not anything, but if you changed some of these subatomic particles, and we'll talk about those. For example, if you change the number of protons in that atom, you no longer have carbon, you would have a different element. When you take a look at the periodic table, you'll see that there are 92 naturally occurring elements that are listed on the periodic table. Those are found in nature. There are more listed. There are more elements listed on the periodic table, but anything above 92 are created. They're synthetic. They're man-made elements that are usually created in some kind of lab and are usually radioactive, and so they decay, and we'll talk about those terms as well. And so they have a kind of a finite existence there. There's six main elements when you're talking about living organisms, six main elements that kind of make up the majority of the body. And these are listed there for you: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. All right, I've used this term already, but an atom is the smallest part of the element. It still has the same properties of that element, and it is comprised of smaller particles, subatomic particles. Most of you have heard of these: protons, neutrons, electrons. Again, this is not a chemistry class, but we need to kind of understand a little bit about these. Some basic things here, and I'll show you a little diagram. The atom would have a centrally located nucleus. which contains protons and neutrons. So that's their location, is in the nucleus. Protons, this is their charge. They are positively charged. They have an overall positive electric charge. Neutrons are neutral, so there's no charge associated with neutrons. And then outside of the nucleus, you would find electrons. Electrons are negatively charged. And we'll talk about where they're located. Technically, they are in what are called electron shells or orbitals. And in figure 2.2, you can kind of see just a basic little diagram here. We'll see some other diagrams, but you can kind of see it has a, this would be the diagram of an atom. You got electrons on the outside. They kind of orbit in a cloud. That's why this looks kind of fuzzy over here on part A. So the electrons would kind of, kind of zip around that outer shell here. In this case, it only has one shell, one layer to it. The atom has a nucleus in the middle or in the central area, and that's where you're going to find protons and neutrons. So this particular drawing here has two protons, has two neutrons, and that represents the an atom of helium, because that's determined by the number of protons. The table here kind of explains exactly what I've just been talking about. It just kind of puts it in table form. If you look at a proton, it's got an electric charge of 1. So it's positively charged. It has a mass of 1, and so it has a measurable mass, and then its location is inside of the nucleus. Neutron, we said already that it's neutral, so there's no charge associated with it. It also has a mass of 1, so it's the same mass or same weight there as the proton, and then it's also located in the nucleus. The electron is a little different. Electrons have a negative charge. There's no real measurable mass associated with electrons, and so they've just given a mass unit of 0, and they're located outside of the nucleus in what's called the electron shell. And we'll talk more about that as we go through the chapter. A couple of terms here that you need to know. The atomic symbol, that's just the letter that represents the name of the element that you'll see on the periodic table, or if you're making notations for hydrogen, you would use the letter H. And most everybody's familiar with H2O as water. And so it has 2 atoms of hydrogen and 1 atom of oxygen. But H is hydrogen. Sodium is represented Na. And so if you're wondering why sodium is not SO, most of the atomic symbols come from the Latin name of the element. And so it just so happens that sodium, the Latin name for sodium is natrium, which is kind of strange, but natrium is sodium, and that's where the Na actually comes from. But and then carbon is C. Very easy. 3 here terms you should be familiar with. The atomic number, you probably may have seen this before. Atomic number basically is the number of protons. And I'll show you where you'll find that on the periodic table in just a minute. But the number of protons defines that particular element. Like I said before, if you change the number of protons, if you change the atomic number, then you've changed the atom. You're no longer looking at, hydrogen has 1 proton, but if I change that to 2, I don't have hydrogen anymore, I have helium. And so the atomic number is very important. The mass number, remember we said that 2 of those subatomic particles have mass. Protons, here it is, protons and neutrons both have mass. And so if you look at the mass number, you're basically looking at essentially the number of protons and neutrons that reside in the nucleus. If you add up the total mass of the protons and the neutrons in the nucleus, you'll have the mass number. Sometimes you see the term atomic mass listed there, and most of the time that's about what the mass number is. But as we'll see in a little while, you have things called isotopes, and there are versions, I guess, of atoms that have different numbers of neutrons. And so what they do is they kind of take an average. And so sometimes you'll see a atomic mass number that has like 1.000 or 1.004 or 5 or something. It's a little not exactly equal to the atomic number, but usually it's very close. Here's an example of a symbol that you would see. So the atomic symbol for this element is listed there, C, so that's carbon. The atomic, if it's written in this notation, the atomic number is on the bottom. And so again, that tells me that I've got 6 protons. Carbon has, in its natural state, in its neutral state, it has 6 protons. Again, in its neutral state, it's going to have the number of protons would also equal the number of electrons. And so you could say by looking at this that carbon here has 6 protons. It would also have 6 electrons. Notice its mass number is 12. Remember that the mass number includes protons and neutrons. And so I can do a little quick math, and that tells me that not only does carbon have 6 protons, but it must also have 6 neutrons, because if I add those together, I'll get a total mass number of 12. Now, periodic table, most everybody's seen an example of the periodic table. I'll show you, this is an abbreviated version of it. They've left off kind of the middle section there. The transition metals section is not listed here, but this simplifies some of this just a little bit so we can look at a few things. A couple of things. One is you see the atomic number listed there. So number 1, see the symbol, this is hydrogen. And you can see the atomic mass. Notice for hydrogen, it's 1.008. And that tells me that there must be an isotope, and there are a couple of isotopes of hydrogen that have different numbers of neutrons. And again, we'll mention that in a minute. But and then helium is listed there for you. Atomic number is 2. That tells me that helium has 2 protons. The mass number is approximately 4. And so that means helium must have 2 neutrons, and so that gives you a total mass number of 4. Okay, you can see lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. You kind of keep going. The other thing you can see here are the groups. The groups are basically columns. Okay, and the groups have Roman numerals designating which group you're looking at. 1 through 8 are the groups. And number 1 is listed there, group 1, group 2, 3, and on down till you get to group 8. And then periods are essentially rows going across. And if you take a chemistry class, you'll go into a little bit more detail about, let's look at, group 1 and see what the characteristics are, because these are not just haphazardly arranged. These are arranged based on the certain characteristics of these atoms and these elements. And so the atoms here, the elements hydrogen, lithium, sodium, potassium, they have similar characteristics. All right, they have similar properties, and so that's why that they fall into this group. And group 2, 3, 4, group 8, these are what are called the inert noble gases. They're very inert. In other words, they don't react very much. And so, if at all, and so they have very similar properties from each one: helium and neon and argon and krypton, and there's a few more on down. But they are arranged based on certain characteristics, and that's kind of what all of this is telling you right there. You can kind of go back and look at this in the notes there. I mentioned before that some elements are radioactive. And so they're given the term isotope. That's a good definition to know. You may see a question about this on the test. Atoms of the same element that have a different number of neutrons. And what that means is, remember that I said if you change the number of protons, you change the element. But if you have a different number of neutrons, you can change that without changing the element, but you do change some of its properties. So for example, down here at the bottom, we have our normal carbon we just looked at. That same symbol, you got carbon, I've got 6 protons. I've got the mass number is 12, so that means I have 6 neutrons. But what happens if we add a neutron to it? It would look like this. This is carbon 13, and it's still, notice it still has 6 protons. I didn't change that, but you've added a neutron, and so now the mass number has changed to 13. Same thing about carbon 14. You may have heard of carbon 14. This is used, and we'll see this later in the semester, but this is used in what's called radioactive dating. They can know properties of this isotope, how quickly this decays. In other words, this is radioactive. It's trying to get back down to its kind of a neutral form, back down to carbon 12, and that takes a certain number, in this case of years, to decay. And so they can use this to help to date fossils of living organisms. And so again, this is carbon 14. That 14 is its mass number. And what that tells us is carbon has 6 protons, so this must have 8 neutrons in it. Okay. And so isotopes are very important in dating things. They're also very important in nuclear medicine because they do emit radiation. Just a couple things about electrons and energy. Electrons are attracted to the positively charged nucleus, right? Opposite charges attract. You got the nucleus that's essentially positive, overall positive charge in the nucleus. That's where the protons reside. The electrons out on the energy level. So what keeps them from just coming together? Why are the electrons still kind of out in that shell? Well, there's an energy force that's kind of essentially keeping them apart. And so again, you would probably talk more about this in a chemistry class, perhaps even a physics class if you take that. But there's a certain amount of potential energy that's essentially keeping those electrons out in that shell and keeping them from being attracted and falling back down into the nucleus there. Now, one way that you can kind of visualize the location of electrons is something known as the Bohr model. I'm going to skip ahead and kind of show you what that looks like. And so here's some of the 6 main atoms or elements we talked about that are especially important in living things: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. And so, of course, you've got the nucleus there. In these diagrams, it doesn't show you, it doesn't really outline the protons and neutrons, but it tells us, we know based on the symbol, how many you should have. And so hydrogen is a little different because based on its symbol here, we know it has 1 proton, but notice that its mass is also 1. So what that means is hydrogen doesn't have any neutrons associated with this stable form of hydrogen. And so it does have 1 electron. Again, remember the number in a neutral atom, the number of electrons are going to equal the number of protons. So 1 proton and 1 electron. And then here is, according to the Bohr model, this is where the electron would be out in an electron shell out here. And then we see carbon. That's a little bit more complex, I guess. It has 2 electron shells. Notice that it lists this outer electron shell as what's called a valence shell. I have that definition for you. That's basically just the outer electron shell there. So you have 2 shells. You have an inner shell that has 2 electrons, and you've got the outer shell for carbon has 4 electrons. And so again, if we look at our chemical symbol here, we know carbon has 6 protons. They're in the nucleus. This is a stable form. This is not radioactive, so it has 6 neutrons. That's also in the nucleus. Because it has 6 protons, and because we're dealing with a neutral atom, in other words, it's not positively or negatively charged, it's neutral, it's going to have, you would expect it to have 6 electrons. And so you can count up and see if you see all 6 electrons. We've got 2 in the inner energy level there, and you've got 4 on the outside. So that gives us a total of 6 electrons. And so you can kind of keep adding and kind of looking at each one of these. Nitrogen has total 7. It's got 5 valence electrons because those are the 5 that are on the outer energy level. Notice oxygen. It has everything. One thing I forgot to mention is this inner shell can only have 2 electrons. Okay, so here, starting with in this diagram anyway, carbon, you can only have 2 electrons on the inner energy level. That's why nitrogen only has 2, oxygen, phosphorus, sulfur only have 2 electrons. And then you can have up to 8 on any of these other electrons. 1, 2, 3, 4, 5, 6. Oxygen only has 6, but notice phosphorus here, 1, 2, 3, 4, 5, 6, 7, 8. Phosphorus has a complete second level. So its second energy electron level here has a full complement of 8. And then it had extra ones left over, and so that goes to the next outer. So now the valence electron shell here is this outer energy level, 1, 2, 3, 4, 5. So for phosphorus, it would have 5 electrons out here. So hopefully you kind of see the pattern a little bit. A lot of that is described here. Electrons revolve around the nucleus in the energy shells we talked about. Any of the atoms with atomic numbers of 20 or less, which basically covers, most of those biological, well, all of these that we just looked at, have 20 or less of the atomic number. Atomic number for sulfur was 16 right there, so it should also have 16 electrons. There are a few rules that apply. The first energy shell only holds up to 2 electrons. We mentioned that. Each additional shell can hold up to 8 electrons, shows you that. Each lower shell is filled first before electrons are placed in the next shell. Now, those outer energy levels, that valence shell, is important because that determines a lot of the chemical properties of that atom, especially whether or not it's going to react with and form a chemical bond. And so we're going to see that. The octet rule, that word octet refers to 8. And so the octet rule says that an atom is the most stable whenever it has a full valence electron shell. In other words, when that outermost shell has a complement of 8 electrons, then you'll have the most stable atom that you can have. Of course, the exception is if the atom only has a single shell, like hydrogen, helium, then remember the innermost shell that it has can only have 2, and so hydrogen would have 1 electron here on its energy valence shell, its outer shell here, and then helium would have 2. Okay, let's look at a few things for section 2. We've got a couple of terms here, molecules and compounds. So far, we've been talking about, atoms, single atoms of elements. And so, but now, the question is, what happens if you combine atoms together? Well, if you put 2 or more atoms together, you have a molecule. And there's some examples of molecules here. This is a relatively large molecule. It's very important in biological life. This is glucose. Now, it'll be good to get to know this. We'll talk about this as we go through some of the early chapters. C6H12O6 is glucose. H2 is hydrogen. And then, of course, N is nitrogen. Another way to think about a molecule is the smallest part of a compound that retains its chemical properties. So how does this distinguish from a compound? Right. Well, a compound is a molecule. So a compound is a type of molecule containing at least 2 different elements bonded together. You got to have at least 2 different elements. So if you look at these examples, I have 2 different elements. I've got carbon and oxygen. For water, I've got hydrogen and oxygen. For glucose, I've got carbon, hydrogen, and oxygen. So I've got at least two different elements put together that makes this a compound. So even though the definitions, they kind of overlap just a little bit, you can think of it this way: all compounds are technically molecules by definition. And if it says it right here, a compound is a molecule. Why is a compound a molecule? Well, let's go back up and look. Compound is a molecule because a compound has at least 2 atoms put together. That's what you have to form a molecule. But notice that not all molecules are by definition compounds, right? Because by definition, a compound has to have 2 different elements put together. And so these are all molecules here. Glucose is a molecule, hydrogen bonded to itself is a molecule, nitrogen bonded to itself, oxygen bonded to itself. That's called diatomic, has 2 atoms. These are all molecules, but they're not all compounds, mainly because hydrogen and nitrogen bonded together only have 1 atom. 1 element is represented there. So to be a compound, you have to have at least 2 different elements put together. So even though there's a little overlap in the definitions there are some things like that distinguish it. When you look at a chemical formula, that includes the number of each. And so again, this is glucose. This is 1 molecule of glucose, and it contains 6, because of that 6 there. In the subscript there, that means I've got 6 carbons, 12 hydrogens, and 6 oxygens that make up that single molecule of glucose. Now, you can, of course, put certain atoms together, and certain atoms will create a bond. That process of creating the bond that holds those two atoms together is what's known as a chemical reaction. We'll talk about a couple different types of bonds. For example, an ionic bond. You need to know what an ion is. I've been talking about having neutral atoms, but what happens if an atom either loses an electron or gains an electron? It forms what's called an ion. It has now a charge associated with it. If you lose an electron, you lose some negativity, and so you're going to have a positive ion. That's also known as a cation. If you gain an electron, you gain some negativity, and so you'll have an overall negative charge, and so that's an ion, and so that's a negative ion. That's called an anion. And then when you form a bond with this, with two ions that are have oppositely charged ions associated with it, then you form an ionic bond. The classic example of ionic bond is sodium chloride. Maybe you've heard of that before. That's salt. And so let's kind of look at the formation of sodium chloride. I've got a sodium atom here. Excuse me. If you notice, the sodium atom has 1 electron on its outer energy level, one electron here. What that means, and when you take chemistry, you'll talk about this, that means this sodium is very reactive. Doesn't like to have, remember, it would like to have 8. 8, according to the octet rule, means has 8 electrons on its outer energy level. That makes it the most stable. This is not very stable because it has one electron on its valence shell. All right, chlorine, count those up, 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 electrons on its valence shell. That's very reactive as well, because remember, it wants to have 8. It's very close to having 8, but it's not quite there yet. So what happens is, if you transfer this electron here to chlorine, now you can kind of create a situation where you have this sodium. It's almost like it now gets rid of that extra electron, and now it's more stable because it has 8 on this outer shell, 8 electrons on its outer shell. So now it's a lot more stable. Chlorine's happy now because it has gained an electron and kind of fills up its outer shell with that electron. So it has a complete outer shell now. So now you got 2 ions. As long as they work together like that, that creates an ionic bond, and it forms a very stable compound that we call salt. Okay. Covalent bonds, that's another way that you can combine atoms to form a very stable bond. But in this case, instead of transferring electrons over, essentially you form kind of a union, a shared union between the 2 atoms. And some covalent bonds are what are called polar. Some of them are nonpolar. Nonpolar, they don't share the atoms equally. Nonpolar shares the atoms equally, such as hydrogen. In other words, when you have 2 atoms, this would be called diatomic. When you have 2 atoms of hydrogen that come together, they share everything equally, share all the electrons equally. Oxygen does the same thing, and that forms nonpolar covalent bonds. And this is kind of showing you, it's kind of hard to see here in the video, but look sometime at figure 2.8, kind of shows you this. It's almost like just perfect sharing. Remember, hydrogen, it's only got 1 electron on its outer energy level. So it's very unstable, but if it finds another hydrogen, it will very quickly form a covalent bond. And now they share, each of those electrons are shared between them equally. And so now it's almost like each one has a complete outer energy level of 2 electrons. Oxygen kind of does the same thing. This is the molecule of methane, which is CH4. It kind of does the same thing. And now, it's trying to get to a stable, this is a very stable molecule. It's trying to get to a stable valence shell valence electron shell. And that happens here because now you essentially have 8 electrons on that outer energy level. Those that are polar still share electrons, but they're not an equal sharing, and so that creates something called electronegativity. The classic example here is water, and that creates some very unique and very important properties. This is a diagram of water. We know the formula is H2O, but notice it's kind of off balance, and so that means you have some electronegativity. In other words, you've got the hydrogen, which is a little bit positive here, so it has a partial positive charge. That's what the little delta symbol there means. Delta plus has a little positive charge there. The oxygen still has a little bit of negative charge associated with that molecule, and that creates some very unique properties that we're going to see here in section 3. So water is a good example of a polar molecule. That means it has the ability to form other bonds, hydrogen bonds. Let's see if there's a picture here. I don't have a picture of water attracting itself, but like if you could imagine other molecules of water side by side, other H2O side by side, the positive of the hydrogen will kind of attract the negative areas of that oxygen. And that kind of creates a little, attraction between those molecules. So they have attraction to each other. That attraction gives it some very important properties. And so we're going to talk about some of those. This is what it's talking about, attraction here. The water molecules essentially are clinging together. They're kind of pulling on each other. And so one property is that water has a high heat capacity. It has the ability, because of this arrangement, this electronegativity, has the ability to absorb a lot of energy without changing the temperature a lot. You may not realize it. You have probably seen this before. You just may not have called it a high heat capacity. But in other words, if you've got some water, it takes water a relatively long time to heat up if you're trying to heat up water. And then once it's warm, it actually retains its energy quite a bit. And so the change in temperature, the drop in temperature is relatively slow as well. And that's very important for living organisms because our bodies have to have this water, but we need that water to have a very stable type temperature. We don't need a lot of fluctuations in our body temperature. We want to have that, 98.6 degrees Fahrenheit temperature, 37 Celsius temperature to maintain the chemical reactions going on in our body. And so we don't need a lot of fluctuation. So it has a high heat capacity. Anybody that has a swimming pool knows that, you put your cold water in at the beginning of the season, and it always seems like it takes a long time for that water to increase in temperature. And that's part of the high heat capacity. Water has a high heat of evaporation. And so, in other words, it takes some time to evaporate, but when it does, it cools off. It transfers heat from the body. So, our bodies will sweat, and then whenever that sweat evaporates, it takes some of the surface, energy or surface temperature along with it. Water is a good solvent. It's sometimes referred to as a universal solvent. It's an excellent solvent. It's able to dissolve especially other polar substances. And there's a couple of definitions there. A solution contains dissolved substances, and those dissolved substances are called solutes. Water molecules are cohesive and adhesive. There's a couple questions on this vocab on the exam. Cohesion, just a vocabulary word. Means together, and so water molecules cling and stick to each other, and so this kind of means that water flows very easily. Water, moves very easily because it's sticking to each other. This is basically why siphon type action would work, is because water is sticking to each other, and then you start kind of a siphon going, and the water kind of pulls the next molecule with it. Also is why water creates a lot of surface tension. And so surface tension kind of creates a little bit of some tension along the surface of a body of water. Maybe you've seen, things floating on water, or like an insect kind of, skipping across the water because of the high surface tension of the water there. Adhesion is water molecules cling to other types of surfaces. And so adhesion means it sticks together. Ad means other, so adhesion is sticking to other surfaces, not just to itself. Capillary action, that's water moving up a tube. You can think of capillary action kind of like a straw. It wants to stick not only to itself, but it wants to stick to kind of or adhere to the surface of the vessel that it's in. And so this is very important for us, as we have blood vessels, and so a lot of your blood contains water, and so well, it's about 50%, and so you've got blood flowing through your vessels, and it's kind of adhering to the sides of the vessels. Plants kind of do the same thing with water. Water, as it goes up the stem of the plant, is based on these main properties: cohesion, water sticking to itself; adhesion and capillary action, water sticking to the sides of the vessels in plants. Everybody probably realizes this, that frozen water, ice, is less dense than liquid water. This is why ice floats, and so that's because of the hydrogen bonds. And so when water freezes below 4 degrees, hydrogen bonds kind of become a little more rigid, but they have more open spaces, and the open spaces allows that frozen water to actually float. All right, the last section we look at would be talking about acids and bases in section 4. And a couple of main important terms we'll look at here. Most everybody probably have seen the term pH, or the abbreviation of pH here, but you may not realize what it stands for, or what it's really trying to measure. We know the pH, or you may know that pH is measuring, whether or not you have an acid or base. It really does stand for something. The P stands for potential. A lot of people substitute the word power there, the potential of hydrogen, or the power of hydrogen, if you want to think of it that way. You're essentially measuring the hydrogen ion concentration in a particular solution whenever you're looking at the pH. In other words, you want to measure how much hydrogen ions, how many hydrogen ions do I have? It turns out the more hydrogen ions you have, the more acidic that solution is. And the fewer hydrogen ions you have, the less acidic or more basic that you have. And so whenever you have water, water will dissociate into hydrogen ions and then hydroxide ions, which is OH minus. And so there's different ways in chemistry, there's different ways to define what an acid is and what a base is. This is usually the definition that we see in when we study about biological organisms. Acids are substances that dissociate in water. In other words, they ionize, they split into ions, and they release hydrogen ions. And so you may be familiar with an acid called hydrochloric acid, HCl. When you have HCl in a solution of water, the hydrogen separates, the hydrogen is released or dissociates or ionizes in that water, so the hydrogen creates the acid. A base is a substance that generally takes up hydrogen ions, so it's almost like a sponge. It kind of absorbs the hydrogen ions in a solution, or you can also think of it as releasing hydroxide, the OH, into the solution. So most everybody has probably seen the pH scale, and we know that the pH scale is basically used to indicate whether or not a solution is acid or basic or alkaline. But we'll kind of talk about a few things here, and then I'll show you the figure, the diagram of the pH scale. On the pH scale, the values do range from 0 to 14. 0 to under 7 is acidic. 7 is considered to be neutral, and we're talking about 7.0 being neutral. Anything above 7 up to 14 is going to be basic, or sometimes you see the term alkaline. And so if you see something that's even like 7.2 or 7.4, that's not neutral. That's basic, even though it's only slightly basic. If it's above 7, even by decimal, then it's considered to be basic. Anything that's below 7. So if it's 6.8, that's very close to 7, but it's still acidic. It's very slightly acidic, but it is acidic. The other thing is we need to understand, a lot of folks don't understand that the pH scale is actually a log scale. In other words, you change 1 unit of pH really represents a 10-fold change in how many hydrogen ions you have, how concentrated the hydrogen ions are. So for example, if you're comparing 2 solutions, all right, one is pH 4, I know that's an acid. One of them is pH 5, that's also an acid. The pH 4 solution is 10 times more acidic than something that's pH 5 because it has 10 times more hydrogen ions in it. Okay, but if you compare something that's pH 5, I know that's acidic, with something that's pH of 7, such as pure water, that's neutral, you could say that the solution that's pH 5 is 100 times more acidic, even though they're only 2 steps different on the pH scale. It's 100 times more acidic. There's 100 times more hydrogen ions in the solution with pH 5. And so some of this is outlined here for you. You've got the pH scale running from 0 to 14. 7 is neutral, and that is basically like pure water. And then anything below 7 is going to be acidic. So you've got some examples of some acid examples here. And then anything above 7 is going to be basic or alkaline. You have some examples there for you. Right. On the side here, you also see the hydrogen ion concentration that's listed there for you as well. All right, last term I wanted to look at here is a buffer. A buffer, you may have heard of this before. This is some type of chemical that tries to limit how much the pH changes. It tries to kind of prevent or try to keep pH from changing. So it tries to keep the pH in a normal area. Buffers are very important for living organisms. They're very important for us. Our normal pH of our blood, for example, is around 7.35 to 7.45, or you could say somewhere close to 7.4. Now, that's not neutral. That's slightly basic. It's just a little bit above neutral, so it's slightly basic. And so you have, if that pH changes even so slightly, doesn't look like a lot, but if the blood pH drops below 7, if it goes above 7.8, so even a small change in pH, you have some very serious conditions. Acidosis, it becomes more acidic. Alkalosis, if it becomes more basic. And so these are very serious. And so your body has, and living organisms have buffers that help to try to prevent big changes in your pH. And so one of the main buffers in living organisms is something called carbonic acid, and it helps to try to maintain the relatively normal, that relatively basic pH, slightly basic pH of 7.4 in the blood.